Did you know that some of the most important battles of World War II were won not by bigger guns, but by smaller ideas? A special kind of paint, a weird looking mortar, a tiny metal box that could cook a potato. These things don't sound like weapons, but they changed everything. We often hear about the giant aircraft carriers and the powerful battleships. They are the stars of the show. But behind the scenes, scientists and engineers were in a hidden war. A war of ideas. They were creating strange new technologies. Many of these inventions were top secret. They were used in quiet, clever ways. They gave one side an edge the other side never saw coming. How do you find a submarine hiding deep in the dark ocean? How do you supply an entire army on a beach with no port? How do you make a torpedo that can hear its target? The answers to these questions are not in the usual history books. They are in the forgotten blueprints, the declassified reports, and the stories of the people who built them. This is the story of 16 of those little-known technologies, the ones that really made the difference. Number 16, what if a shell knew when to explode? Imagine you're trying to shoot down an airplane. The plane is fast. It's moving in 3 dimensions. You're firing shells from a gun. For your shell to work, one of 2 things has to happen. You either score a direct hit, which is incredibly difficult, or you set a timer on your shell, you guess the altitude of the plane and set the fuse to explode at that height. If you guess right and the plane flies through the shrapnel, you win. But most of the time you guess wrong. The shell explodes in empty air. It was a problem that frustrated naval gunners to no end. They were filling the sky with metal, but most of it was useless. The solution was something out of science fiction. It was called the proximity fuse, or the VT fuse for variable time. The idea was simple. What if the shell itself could tell when it was near a target? What if it could decide on its own when to detonate for maximum effect? To do this, it would need a brain and eyes. The eyes were a tiny radio transmitter and receiver tucked into the nose of the shell. Miniature radar. The development was a monumental task. A team led by the physicist Merle Tuve at the Johns Hopkins University's Applied Physics Laboratory took on the challenge in 1940. They called themselves Section T. The problem seemed impossible. They had to build a complete radio set with delicate vacuum tubes and batteries that could fit in the palm of your hand. And this tiny radio had to survive being fired out of a cannon. The force of the launch was immense, around 20,000 times the force of gravity. Early vacuum tubes shattered into dust. The team had to redesign them from scratch using stronger materials and new construction methods. They created tiny, rugged tubes that could take the punishment. They developed special batteries that were only activated by the spin of the shell after it was fired. By 1942, they had a working prototype, but the technology was so secret, they were terrified the enemy might get their hands on a dud. A non-exploding shell could be recovered, studied, and copied. So its first use was carefully controlled. It was only allowed to be used over water, where any duds would sink to the bottom of the ocean. The first real test came in January 1943. The light cruiser USS Helena was in the Pacific. It used its new proximity fuse shells to shoot down a Japanese dive bomber on the first pass. The gunners were stunned. The effect was immediate and dramatic. The numbers tell the story. Standard time fused shells required, on average, over 2,000 rounds to bring down a single aircraft. With the proximity fuse, that number dropped to under 500, and in some cases, much lower. Against the V-1 flying bombs aimed at London, the fuses were a miracle. In the last week of the attack, anti-aircraft batteries using these shells were downing 79% of the V-1s that entered their range. When they were finally cleared for use over land during the Battle of the Bulge, they had a terrifying new effect. Set to explode just above the ground, they showered enemy soldiers in trenches with shrapnel. There was no place to hide. The proximity fuse was a quiet revolution. It was never as famous as the atom bomb, but some military analysts believe it was just as important. It was a tiny electronic brain that turned every shell into a smart weapon. But what don't we know? How many prototypes were lost during testing in the deserts of New Mexico, and did any enemy agents ever get close to finding one? The official story is that the secret was kept perfectly, but is that really possible? And what happened to the millions of unused fuses after the war? Did their circuits inspire the next generation of electronics, or were they simply scrapped? The history of this tiny device is full of circuits, but some of them are still open. Number 15, how do you kill a submarine you can't see? For the first few years of the war, hunting a submarine was a frustrating game of cat and mouse. A destroyer would detect a U-boat with its sonar, or ASDIC as the British called it. The destroyer would then race towards the location. The problem was the depth charge. These were big barrels of explosives rolled off the back of the ship. They were set to explode at a certain depth, but to use them, the destroyer had to pass directly over the submarine's position. And at that final moment, the sonar would lose contact. The noise of the ship's own engines and the turbulence of the water created a blind spot directly below. The captain was effectively guessing. He was dropping explosives into a huge volume of water, hoping to get lucky. The U-boat commander knew this. He could make a sharp turn or a dive at the last second. Most depth charges, over 95% of them, exploded harmlessly in the water. A new weapon was needed, something that could be fired forward while the hunter could still see the prey on its sonar. The answer was a strange-looking weapon called the Hedgehog. It was not an explosive. Not at first. It was a type of spigot mortar. Imagine a metal plate with 24 short poles or spigots sticking out of it. On each spigot, you place a small 65-pound bomb. The bombs are then fired forward all at once in a circular pattern. They would fly through the air and land in the water up to 250 yards in front of the ship. Here was the clever part. The Hedgehog bombs only exploded on contact. They were not set to a certain depth. If a bomb hit the hard metal hull of the submarine, it would detonate. Its 35 pounds of Torpex explosive was enough to punch a hole in the pressure hull. If the bombs missed, they would simply sink to the bottom without exploding. This had a huge psychological advantage. With depth charges, the massive underwater explosions would shake both the hunter and the hunted. The destroyer crew wouldn't know if they had hit anything until they saw oil or debris surface. With the Hedgehog, silence meant failure. A single explosion meant a direct hit. There was no ambiguity. The weapon was developed by the Royal Navy's Directorate of Miscellaneous Weapons Development, a group fittingly known as the Weasers and Dodgers. It was introduced into service in late 1942. At first, naval captains were skeptical. They were used to the thunderous drama of depth charges. The quietness of a Hedgehog miss was unsettling. But as crews got trained, its effectiveness became clear. A study by the U.S. Navy's Operations Research Group found that in a sample of attacks, depth charges had a kill rate of around 7%. The Hedgehog had a kill rate of over 40%. It didn't just damage submarines, it destroyed them. The Hedgehog changed submarine hunting from a game of area bombing to one of precision targeting. The destroyer could now stand off, keep the U-boat on its sonar, and fire a pattern of contact-fused projectiles directly at it. There was no last-minute blind spot, no guessing. It was a simple mechanical solution to a complex tactical problem. It was one of the key technologies that helped turn the tide in the Battle of the Atlantic, but questions remain. The initial adoption of the Hedgehog was slow. Was this just due to naval conservatism, or were there early technical failures that have been glossed over in the official histories? We know the statistics of its success, but how many friendly ships were damaged by accidental detonations or malfunctions? And with a weapon designed to be silent on a miss, how many U-boats were hit by a single projectile, damaged but not sunk, and managed to limp home, their crews carrying the secret of a new, terrifying weapon they had just encountered? Number 14, could you see radio waves? In the vast emptiness of the Atlantic Ocean, a convoy of merchant ships was a vulnerable target. Lurking somewhere beneath the waves were groups of U-boats. To coordinate their attacks, these U-boats had to communicate. They would surface, usually at night, and send short, coded radio messages to their headquarters and to each other. These messages were their lifeline. They were also their biggest weakness. The Allies were already reading many of these messages thanks to the codebreakers at Bletchley Park. But that process took time. Sometimes hours, sometimes days. By the time a message was decrypted, the U-boat could be 100 miles away. What was needed was a way to find the U-boat the moment it transmitted. They needed to be able to see the radio waves. The technology that made this possible was called high-frequency direction finding, or HFDF. The sailors who used it just called it Huff-Duff. The concept was not new. Direction finding had been around since the early 1900s. It worked by using a special antenna to find the direction a radio signal was coming from. But early systems were slow and clumsy. They required the operator to manually rotate a large antenna, listening for the signal to be at its strongest or weakest. This could take a minute or more. A U-boat's transmission was often less than 30 seconds long. The old technology was useless. The breakthrough came from a team of French and British engineers led by Robert Watson Watt, the same man who pioneered radar. They developed a new kind of system that used a set of fixed antennas and a cathode ray tube display, the same kind of screen used in early televisions and oscilloscopes. When a radio signal was received, it would instantly appear on the screen as a line or an ellipse. The orientation of the line on the screen pointed directly to the bearing of the transmission. It was instantaneous. The operator didn't need to turn anything. He just had to see the blip on the screen and read the bearing off a scale. The whole process took seconds. Starting in 1942, Huff-Duff sets were installed on naval escorts. The effect was immediate. When a U-boat surfaced to send a message, the radio operator on a nearby destroyer would see a spike on his screen, and he would call out the bearing. If another ship in the convoy also got a bearing, they could plot the two lines on a map. Where the lines crossed was the location of the U-boat. An escort could be sent to investigate, forcing the submarine to dive and lose contact with the convoy, or even better, to attack it. Huff-Duff was a silent killer. The U-boat crews had no idea they were being tracked. They believed their short transmissions were safe. They couldn't understand how Allied destroyers seemed to appear out of nowhere, right on top of them, in the middle of the vast ocean. Historian Patrick Beasley, who worked in naval intelligence, wrote in his book, Very Special Intelligence, that the German belief in the invisibility of their U-boat transmissions was a fatal error. Huff-Duff was responsible for directly or indirectly leading to the sinking of about a quarter of all U-boats destroyed during the war. It was arguably more effective in real-time tactical situations than the more famous Enigma decrypts. But what mysteries still surround Huff-Duff? The technology was top secret. How were the operators trained so quickly and on such a large scale without the secret leaking out? We know of its successes, but were there instances where spoofed or reflected signals sent escort ships on wild goose chases, leaving the convoy undefended? And perhaps most intriguingly, did German naval intelligence ever capture a Huff-Duff set or its manuals? And if so, why did they fail to grasp its significance? The airwaves were a battlefield, and the full history of that electronic war is still not fully written. Number 13. What was the secret inside the little black box? Radar was one of the most important technologies of the war, but early radar had a big problem. It was clumsy. It used long radio waves, which meant it needed large antennas. It was good at detecting big things like ships or formations of bombers at long range. But it was not good at detecting small things. A surfaced submarine with only its conning tower showing above the waves was almost invisible to it. So was the periscope of a submerged U-boat. The long waves of the radar would just wash over these small targets. To see smaller objects, you needed a radar that used much shorter wavelengths in the microwave range. This was called centimetric radar. The physics was well understood. The problem was generating a powerful enough microwave signal. The existing vacuum tubes and transmitters couldn't do it. They could produce a trickle of microwave energy, but not the powerful pulse needed for a useful radar. The Allied radar program was stuck. The solution came from an unlikely place, the physics department at the University of Birmingham in England. In early 1942, scientists John Randall and Harry Boot were working on the problem. They were not radar experts. They were just physicists trying to find a better way to generate microwaves. They came up with a new design for a device called a magnetron. It wasn't a completely new idea, but their version was different. It had a series of resonant cavities, little hollows, carved into a block of copper. When electrons were fired past these cavities in a strong magnetic field, they would generate an incredibly powerful and stable microwave signal. They called it the cavity magnetron. Their first prototype was a clunky thing, sealed with wax, but when they turned it on, it worked better than anyone could have dreamed. It produced pulses of microwave energy hundreds of times more powerful than any existing device. A story, possibly apocryphal, says it was powerful enough to cook a potato. It was a quantum leap in technology. It was the key that unlocked centimetric radar. This little metal box was so important that it became the centerpiece of a secret diplomatic mission. In September 1940, the Tizard mission traveled from Britain to the United States. They brought with them a treasure trove of British scientific secrets to share with the still neutral Americans, hoping to get U.S. industrial power involved in producing them. The most important item in their luggage was a single-cavity magnetron, number 12. At first, the American scientists at Bell Labs were skeptical. They were working on their own microwave generators that produced only a few watts of power. The British claimed their little box could produce 10,000 watts. When they tested it, the Americans were stunned. It worked. An enormous research effort was launched at the MIT Radiation Laboratory to develop radar systems based on the magnetron. The result was small, lightweight, powerful radar sets that could be fitted into airplanes and small ships. As an aircraft with this new radar could now see a U-boat conning tower from miles away, even on the darkest night or in thick fog. The submarines lost their cloak of invisibility. They had been safe on the surface at night. Now they were hunted. The introduction of airborne centimetric radar in 1943 had a devastating effect on the U-boat fleet. The German Admiral Karl Donitz wrote in his diary about the sudden, inexplicable increase in U-boat losses. His crews reported being attacked by aircraft that seemed to come out of nowhere without any warning. The cavity magnetron was a war winner. It transformed radar from a defensive early warning system into a precise offensive weapon. And it's still with us today. A simplified version of that same device is probably sitting in your kitchen. It's the heart of your microwave oven, but what parts of its story are still in the shadows? Randall and Boot were not the only ones working on magnetrons. Were there other research paths in other countries that were close to a similar breakthrough? The official story of the Tizard mission is one of smooth cooperation, but were there tensions or rivalries between the British and American scientists that have been written out of the history? And how many early magnetrons failed in spectacular, dangerous ways in the labs before the stable design was perfected? The little black box had a bright future, but its past may still hold some dark corners. Number 12. How do you hide a ship from a mine? At the beginning of the war, the German Navy deployed a new and terrifying weapon. It was the magnetic mine. Unlike older contact mines that had to be physically struck by a ship, these mines sat on the seabed in shallow waters, like the shipping channels of the Thames estuary. They were detonated by a ship's magnetic field. Every large steel ship is, in effect, a giant floating magnet. It acquires a magnetic signature from the Earth's magnetic field during its construction and its voyages. As the ship passed over the mine, a sensor in the mine would detect the change in the local magnetic field and trigger the explosion. It was a deadly threat. The mines were hard to sweep, and they could sink a ship without ever touching it. The British Admiralty was desperate for a solution. A physicist named Charles F. Goodeve, who was part of the Naval Research Department, was tasked with finding a countermeasure. The team started by studying the magnetic signatures of ships. They used sensitive magnetometers to measure the fields of destroyers and battleships as they passed by. They discovered that the signature was predictable. It was mostly a vertical magnetic field. So they asked a simple question. What if you could cancel that field out? What if you could make the ship magnetically invisible? The solution they came up with was called degaussing. It was based on a principle discovered by the German mathematician Carl Friedrich Gauss in the 1830s. The idea was to wrap the ship in a belt of electrical cables. When a current was passed through these cables, it would create an opposing magnetic field. If you got the current just right, this new field would exactly cancel out the ship's own magnetic signature. As to a magnetic mine on the seabed, the ship would simply not be there. It would pass over silently, like a ghost. The first experiments were conducted in late 1939. They wrapped the battleship HMS Nelson with hundreds of feet of copper cable and passed a current through it. It worked. The ship's magnetic field was drastically reduced. The process was quickly rolled out across the entire fleet and the merchant marine. It was a massive undertaking. Thousands of ships, from giant ocean liners to small trawlers, had to be fitted with these degaussing coils. At first, the cables were just strapped to the outside of the hull, creating a distinctive girdle. Later, on new ships, the coils were built directly into the structure of the vessel. The process was sometimes called degaussing or wiping. Degaussing was not a perfect solution. A ship's magnetic field changes depending on its location on the globe and its heading. So the current in the coils had to be constantly adjusted. Ships had to periodically visit special degaussing stations to have their magnetic signatures measured and their equipment calibrated. But it was incredibly effective. It dramatically reduced the threat of the standard magnetic mine. Of course, the mine designers responded by creating more sophisticated triggers, such as acoustic mines that listened for a ship's engines, or pressure mines that detected the change in water pressure as a ship passed overhead. The technological cat and mouse game continued, but degaussing was a crucial first response. It was a clever application of 19th century physics to solve a 20th century problem. It was an invisible shield, a quiet technology that saved thousands of ships and lives. But the history of this technology is not fully transparent. Were there accidents during the installation and testing of these high current electrical systems on steel ships? We know the theory was sound, but how much trial and error was involved in getting the calibration right for different classes of ships? And did any ships, believing themselves to be protected, use faulty or poorly calibrated degaussing gear, leading to their loss? The records of such failures might not have been preserved. The ghost ships of degaussing might have some stories we have yet to hear. Number 11, can a torpedo hear its target? A torpedo is a guided missile, but for most of the war, it was not very smart. It was fired from a submarine or a ship, and it ran in a straight line at a preset depth. Hitting a moving target required complex calculations of speed, angle, and distance. A skilled submarine commander could do it, but misses were common. A torpedo that could guide itself to the target would be a revolution. The Germans were the first to develop a practical version of this idea. It was an acoustic torpedo, codenamed G70s and nicknamed Zonkonig, or Wren. It was introduced in the fall of 1943. This torpedo had a simple acoustic guidance system in its nose. It had two hydrophones, underwater microphones, that listened for the sound of a ship's propellers. The guidance system was designed to steer the torpedo towards the loudest sound it could hear. For a convoy escort ship like a destroyer or a corvette, the loudest sound was its own fast-turning propellers as it raced to protect the merchant ships. The hunter suddenly became the hunted. The effect of this new weapon was immediate and terrifying for Allied sailors. Escort ships that had been the masters of the Atlantic suddenly found themselves being targeted. Torpedoes seemed to change course in the water, turning to follow them. In the first few weeks of its use, the Zonkonig sank several Allied escort vessels. Morale plummeted. How do you fight a weapon that can hear you coming? The Allies were caught by surprise, but they reacted quickly. They knew the torpedo homed in on propeller noise, so the answer had to be to create a louder noise somewhere else. They needed a decoy. The task of developing one was given to research teams in the US and Canada. The result was a device codenamed FXR, but known to all the sailors as Foxer. It was a simple but ingenious noisemaker. It consisted of one or two hollow steel pipes about 5 inches in diameter with holes drilled in them. These pipes were towed on a long cable hundreds of yards behind the ship. As the ship moved, water would rush through the pipes, causing them to vibrate and rattle. This created a huge amount of underwater noise, much louder than the ship's own propellers. When an acoustic torpedo was detected, the escort ship would deploy its Foxer. The torpedo's simple electronic brain would hear two sounds, the ship and the much louder Foxer. It would almost always steer towards the louder sound, the decoy. It would strike the Foxer and explode harmlessly, far behind the ship. Foxer was not a perfect system. It was noisy and clumsy to deploy and retrieve. It also reduced the ship's own ability to use its sonar because its own decoy was making so much noise. And it slowed the ship down, making it harder to maneuver, but it worked. It was a simple mechanical countermeasure to a sophisticated electronic weapon. The introduction of Foxer in late 1943 dramatically reduced the effectiveness of the acoustic torpedo. The cat and mouse game of naval technology had taken another turn. But what parts of this acoustic war are still silent? The development of the Zonkonig was a closely guarded secret. How many failed tests were there? And did any of these early prototypes fall into Allied hands before its official deployment? On the Allied side, the first encounters with the acoustic torpedo must have been terrifying and confusing. Are there logs from ships that were sunk before the nature of the new weapon was understood, containing first-hand accounts of this magic torpedo? And how many sailors' lives were lost due to accidents with the clumsy Foxer gear, a story of the solution being almost as dangerous as the problem? The sounds of that underwater battle have faded, but the echoes of its secrets might still be found. Number 10. How do you put a tank on a beach? In the early stages of the war, amphibious invasions were a nightmare. To capture a coastline, you needed to land a large number of soldiers. But soldiers alone were not enough. They needed support, they needed artillery, they needed supplies, and most of all, they needed tanks. A handful of machine guns in a concrete pillbox could hold off hundreds of infantrymen, but they couldn't stop a tank. The problem was, how do you get a 30-ton tank from a ship onto a hostile beach? The traditional way was to capture a port, but ports were heavily defended. They were obvious targets. An invasion force trying to capture a port would be walking into a meat grinder. The other option was to use cranes on large transport ships to lower tanks into smaller landing craft. This was slow, difficult, and had to be done in calm seas. It was not practical for a large-scale invasion under fire. A new type of ship was needed, something that could carry a whole fleet of tanks across an ocean and then deliver them directly onto a beach. The British Prime Minister Winston Churchill was obsessed with this problem. In a 1940 memo, he demanded a vessel that could handle the depositing of tanks on beaches. This led to the development of the landing ship tank, or LST. The design was a masterpiece of ugly functionality. The LST was essentially a giant floating seagoing shoebox. It had a flat bottom, which allowed it to run right up onto a gently sloping beach. Its most important feature was the huge clamshell doors at the bow. Behind these doors was a long ramp. The ship would beach itself, the bow doors would swing open, the ramp would be lowered, and tanks, trucks, and other vehicles could simply drive off down the ramp and onto the beach, ready to fight. The American and British designers collaborated on the plans. The initial design, the Ellis Tone, was built in Britain. But it was the American shipyards with their immense industrial capacity that would build them by the hundreds. The LST-12, or LST Mark II, became the standard design. Over 1,000 of these ships were built during the war. They were not pretty. They were slow, with a top speed of about 12 knots. Their crews joked that LST stood for Arge Slow Target. But they were incredibly versatile and vital. An LST could carry around 20 tanks in its large open tank deck. The upper deck could carry smaller vehicles or even parts of a disassembled aircraft. They could also be configured to carry hundreds of troops or act as hospital ships. They were the backbone of every major amphibious landing of the war, from Sicily and Anzio in Italy to the massive D-Day landings in Normandy, and across the island-hopping campaigns of the Pacific. General Eisenhower would later write that the LST was one of the most important pieces of equipment that helped win the war. It was a simple, unglamorous ship. It had none of the grace of a destroyer or the power of a battleship. But the LST solved one of the most fundamental problems of modern warfare logistics. It was the delivery truck of the invasion. It made it possible to land not just an army, but a modern mechanized army anywhere in the world. But what is the unwritten history of the LST? These large, slow targets were incredibly vulnerable during beach landings. How many were lost not to enemy fire, but to bad weather, hidden underwater obstacles, or mechanical failures of their bow doors and ramps? The official histories focus on the successes, but the stories of the failed landings and the lost ships are less well known. And what about the crews? What was it like to live and fight on these slow, crowded, and often targeted vessels? The LST was a workhorse, and the stories of its daily grind are likely far more complex and harrowing than the grand strategic histories suggest. Number 9, can you build a port in a week? The D-Day landings in Normandy on June 6, 1944, were the largest amphibious invasion in history, The plan was to land hundreds of thousands of men and thousands of vehicles on the beaches of France. But landing them was only the first problem. An army, as the saying goes, marches on its stomach. It needs a constant supply of food, fuel, ammunition, and reinforcements. A modern army needs thousands of tons of supplies every single day. This kind of tonnage can only be handled by a major port with deep water harbors and large cranes. The Allies knew they could not capture a major port like Cherbourg or Le Havre right away. They would be too heavily defended, and the defenders would likely demolish the port facilities before they were captured. So they faced a dilemma. How do you supply a massive army on a coastline that has no ports? The answer was audacious. If you don't have a port, you build one, and you bring it with you. This was the concept behind the Mulberry Harbors. They were temporary artificial harbors that would be prefabricated in Britain, towed across the English Channel, and assembled off the coast of Normandy. It was one of the most ambitious engineering projects of the entire war. The idea was championed by Winston Churchill and developed by a team of brilliant engineers. The Mulberry Harbors consisted of several key components. The first was a breakwater. This was created by sinking a line of old ships codenamed Gooseberries and huge hollow concrete caissons codenamed Phoenixes. Some of these Phoenix caissons were massive, as tall as a 6-story building. They were built in dry docks in Britain and floated and towed across the channel by tugboats and then sunk in precise locations to create a calm harbor in the rough waters of the channel. Inside this breakwater was the port itself. The piers or roadways were codenamed whales. These were long, floating steel roadways that snaked from the shore out to the pierheads. The pierheads, called spuds, were the unloading platforms. They were large, floating structures with legs that could be lowered to rest on the seabed. This allowed the pierhead to remain at a constant height, while the roadway connected to it could rise and fall with the famous 20-foot Normandy tides. 2 Mulberry Harbors were built. Mulberry A was assembled at Omaha Beach for the American forces, and Mulberry A at Arromanches for the British and Canadian forces. They were operational just a few days after D-Day. They were a miracle of logistics. For a short time, they worked as planned, unloading thousands of tons of supplies. But on June 19th, a massive storm, the worst in 40 years, struck the Normandy coast. Mulberry at Omaha Beach, which was more exposed, was completely destroyed. Mulberry B, later nicknamed Port Winston, was damaged but survived. It was repaired and would go on to be the main supply port for the Allied armies for the next several months. In its peak, it was handling over 10,000 tons of supplies per day. The Mulberry Harbors were a testament to creative engineering. They solved an unsolvable problem. They allowed the Allies to build up their forces in Normandy faster than the enemy could reinforce their own. Without them, the D-Day landings might have succeeded at first, but the armies could have withered on the vine, starved of supplies. But what parts of the Mulberry story have been submerged by history? The project was so vast and complex. It must have been plagued by engineering challenges and failures that were never publicized. How many Phoenix caissons were lost or damaged during the perilous tow across the channel? The destruction of Mulberry A is often blamed solely on the storm, but were there design flaws or assembly errors that contributed to its collapse? And what was the human cost of building these giant structures in the shipyards of Britain? A story of round-the-clock labor that is often overlooked in favor of the military drama. The ruins of the Mulberry Harbor at Arromanches are still visible today, but the full story of their creation and their near failure remains partly hidden. Number 8. How do you run a pipeline under the ocean? Fuel is the lifeblood of a modern mechanized army. The tanks, trucks, and airplanes that spearheaded the Allied invasion of Europe after D-Day consumed fuel at a staggering rate. In the early days of the invasion, this fuel had to be brought ashore in cans and small tankers, a slow and dangerous process. A more efficient and secure method of delivering fuel was desperately needed. The idea that emerged was as simple as it was ambitious. Why not run a pipeline from England under the English Channel directly to the beaches of Normandy? This would create a direct, continuous, and hidden supply line for the fuel. The project was given the code name Pluto, which stood for Pipelines Under the Ocean. The technical challenges were immense. No one had ever laid a high-pressure oil pipeline in the open sea before, especially not in a war zone. Two different types of pipe were developed. The first was a flexible pipe, similar to a submarine telegraph cable, but hollow. It was called Hyas, from the names of the companies that developed it: Hartree, Anglo-Iranian, and Siemens. It was essentially a lead pipe reinforced with layers of steel tape and steel wire armor. The second type was a less flexible but more robust steel pipe, only about 3 inches in diameter. It was called Hamel, after the engineers who designed it. The idea was to weld 40-foot sections of this pipe into incredibly long lengths, and then wind it onto giant floating drums, like thread on a spool. These drums, called conundrums, were enormous, some 50 feet in diameter, and would be towed by tugboats. The project was led by Arthur Hartley, the chief engineer of the Anglo-Iranian Oil Company. The manufacturing was done in secret at factories all over Britain. Special ships were converted to act as pipe layers. The first lines were laid in August 1944, a couple of months after D-Day. They ran from the Isle of Wight to the port of Cherbourg, which had by then been captured. Later, a larger network of 17 pipelines was laid further east across the narrow Strait of Dover to supply the advancing armies. Pluto was an outstanding success. By early 1945, the pipelines were delivering over 1 million gallons of fuel per day to the continent. This fuel was essential for the final push into Germany. The system was so efficient and so secret that enemy intelligence seems to have been completely unaware of its existence. It was a logistical lifeline, hidden on the seabed. It was an unglamorous, invisible part of the war effort, but a critically important one. But what about the parts of the Pluto story that lie buried? The engineering was experimental. How many test pipelines failed, broke, or leaked during development? The process of laying the pipes in the treacherous currents of the English Channel must have been fraught with difficulty and danger. Are there records of failed layings or of conundrums that broke free in storms? And was the secrecy really as perfect as the official histories claim? It seems incredible that such a massive industrial undertaking involving miles of pipe and specialized ships could have gone completely unnoticed. The pipeline itself was silent, but its history may not be. Number 7, could a submarine breathe underwater? A submarine's greatest advantage is stealth, its ability to operate unseen beneath the surface. But World War II submarines had a major weakness: their batteries. The diesel engines that propelled them on the surface and charged their batteries needed air to run. To run submerged, they had to switch to electric motors powered by huge banks of batteries. These batteries had a limited life. After a day or so of submerged running, a submarine had to surface to run its diesel engines and recharge. This was when it was most vulnerable. On the surface, it could be seen by ships and, more importantly, by aircraft with radar. A solution was needed: a way for a submarine to run its diesel engines and recharge its batteries without having to fully surface. The idea that was developed was the snorkel. The concept was simple. It was a long, retractable tube that could be raised above the surface of the water, while the submarine itself remained at periscope depth. The tube was actually 2 pipes. One brought fresh air down to the diesel engines, and the other exhausted the engine fumes. A special valve at the top of the air intake, a float valve, was designed to slam shut if a wave washed over it, preventing the submarine from being flooded. The snorkel was not a new idea. Prototypes had been experimented with by various navies for decades, but it was the German Navy that perfected it and deployed it widely towards the end of the war. They called it the Schnorkel. The first operational snorkels were fitted to U-boats in mid-1943. By 1944, they were becoming standard equipment. The snorkel changed submarine warfare. It allowed a U-boat to stay submerged for weeks, or even its entire patrol. It could travel underwater on its powerful diesel engines, not just crawl along on its quiet but slow electric motors. It was no longer forced to surface at night to charge its batteries, exposing itself to radar-equipped aircraft. The snorkel turned the submarine from a submersible ship into a true underwater vessel. However, it was not a perfect solution. Using the snorkel had significant drawbacks. The submarine was limited to a slow speed, typically less than 6 knots, to prevent the snorkel mast from creating a large, visible wake. The noise of the diesel engines running inside the confined space of the submarine was deafening for the crew. And if the float valve failed, the boat could be quickly flooded with seawater. Worse, the engines would suck air from inside the boat itself, creating a partial vacuum that could cause the crew's ears to pop and even cause internal injuries. There are accounts of crews passing out from lack of oxygen. The snorkel had could also be detected by the new high-frequency centimetric radars. It was a small target, but not an invisible one. Despite these problems, the snorkel gave the U-boat a new lease on life. It allowed them to return to dangerous coastal waters where Allied air power had previously made it impossible for them to operate. It was a simple mechanical device that fundamentally altered the operational capabilities of the submarine. But what are the untold stories of the snorkel? How many submarines were lost due to snorkel malfunctions, either from flooding or from the telltale wake being spotted? The psychological toll on crews, forced to live with the constant deafening roar of the diesels for weeks on end, must have been immense. Are there patrol logs or personal diaries that reveal the true human cost of this technology, and how close were the Allied navies to developing their own effective snorkel technology? The history of this breathing tube is one of adaptation and survival, but it is also a story of a difficult and dangerous compromise. Number 6. What was the truth about the perfect submarine detector? From the very first day of the war in the Atlantic, the primary tool for hunting submarines was ASDIC. The British called it this after the Anti-Submarine Detection Investigation Committee that developed it. The Americans called it by its more familiar name, sonar. The principle was simple. The device sent out a pulse of sound, a ping, into the water. This sound wave would travel outwards, and if it hit an object like a submarine, it would bounce back as an echo. The operator, listening on headphones, would hear the ping echo. By measuring the time it took for the echo to return, he could calculate the distance to the target. By rotating the transmitter, he could find its bearing. To the public, and even to many naval officers, ASDIC seemed like a miracle weapon. It promised to make the oceans transparent, to rob the submarine of its stealth. It was seen as the definitive answer to the U-boat threat. But the reality was very different. ASDIC was a flawed and limited tool. The story of its use is a story of frustration and a steep learning curve. One of its biggest problems was the water itself. The ocean is not a uniform medium. Changes in temperature and salinity can bend or reflect sound waves, creating shadow zones where a submarine could hide. The sound pulse also reflected off of many other things besides submarines. A school of fish, a whale, or even the wake of another ship could produce a non-sub contact that would send a destroyer on a wild goose chase. A skilled ASDIC operator had to learn to distinguish the firm, metallic echo of a submarine from these false contacts. It was as much an art as a science. ASDIC also had a limited range, typically no more than a mile or so. And as mentioned earlier, it had a blind spot directly underneath the ship. As a destroyer got close to a U-boat to drop depth charges, it would lose contact. Furthermore, a skilled U-boat commander could use the ASDIC against the hunter. When he heard the pings of a searching destroyer, he knew he had been detected. He could then maneuver, dive deep, or even sit silently on the bottom to try and break contact. Despite these limitations, ASDIC was the only tool the Allies had for detecting submerged submarines for the first part of the war. It was the centerpiece of their anti-submarine strategy. The Battle of the Atlantic became a duel between the U-boat commanders and the Allied escort captains and their ASDIC operators. The Allies had to develop new tactics like creeping attacks where one ship would hold the submarine on its ASDIC while another ship, with its own ASDIC turned off, would silently pass over to drop depth charges. They also had to constantly improve the technology, developing systems that could estimate the depth of the target, not just its range and bearing. The story of ASDIC is a caution against believing in wonder weapons. It was not a perfect solution. It was a difficult, temperamental, and often misleading piece of technology, but it was essential. Without it, the convoy escorts would have been truly blind. It was the constant nagging threat of the ASDIC ping that kept the U-boats on the defensive, that forced them to be cautious, and that ultimately, when combined with other technologies like radar and air power, defeated them. But what about the operational details? We don't know. The performance of ASDIC was highly dependent on the skill of the individual operator. Is it possible to know how many U-boats escaped simply because an inexperienced or fatigued operator misread a signal? The official reports focus on successful attacks, but the data on failed attacks and false contacts is much harder to analyze. And how much did the U-boat crews learn about the specific performance characteristics of different OSTIC sets, allowing them to develop tailored evasion tactics? The ping was the sound of the hunt, but the full story of all the sounds the operators heard and all the ones they missed is lost to the ocean. Number 5, could a torpedo be dropped from a plane? A torpedo is a powerful weapon, but it's also a heavy and delicate one. Firing it from a ship or a submarine is one thing. Dropping it from a fast-moving airplane is another. In the early days of naval aviation, this was a major technical problem. If you dropped a standard torpedo from a plane flying at any significant height or speed, one of several bad things would happen. It might break apart when it hit the water, it might dive straight to the bottom, or it might porpoise, bouncing off the surface and flying through the air. The Japanese Navy worked on this problem for years, and by the late 1930s had developed the Type 91 aerial torpedo. This was arguably the most advanced weapon of its kind in the world at the time. What made it special was a set of small wooden fins attached to its tail. These fins, called kyoban, were designed to stabilize the torpedo as it fell through the air. When the torpedo hit the water, the fins would break off. More importantly, the Type 91 had a sophisticated control system that used a gyroscope to prevent it from rolling in the air and to control its angle of entry into the water. This allowed it to be dropped from higher altitudes and at higher speeds than any other aerial torpedo. But the Japanese engineers faced a specific problem in 1941. They were planning the attack on Pearl Harbor. The harbor was very shallow, only about 40 feet deep. A standard aerial torpedo, when dropped, would dive deep into the water before leveling off to run at its target depth. In the shallow waters of Pearl Harbor, the torpedoes would simply bury themselves in the mud at the bottom. To solve this, Japanese engineers, under the direction of Commander Minoru Genda, modified the Type 91 torpedoes. They added larger wooden fins to the tail, which acted like the feathers on an arrow to create more drag and ensure a flatter trajectory. More critically, they attached a wooden breakaway stabilizer to the nose. This device, looking like a small drum, would absorb some of the impact with the water and help the torpedo to level out much more quickly. After extensive testing in the shallow waters of Kagoshima Bay, they perfected a torpedo that could run true in the shallow harbor. On December 7th, 1941, this specialized technology proved devastatingly effective. The torpedo bombers, flying low and slow, dropped their modified torpedoes. These weapons, which the American defenders did not believe could even be used in the harbor, ran straight and true. They were responsible for sinking several of the battleships, including the USS Oklahoma and the USS West Virginia. It was a tactical surprise made possible by a small, clever, and little-known technological modification. Later in the war, the U.S. Navy developed its own highly effective aerial torpedo, the Mark 13. Early versions were notoriously unreliable. But after extensive research, including experiments at the California Institute of Technology, they made 2 key modifications. They added a drag ring to the nose, which slowed the torpedo down and made it hit the water at a better angle. And they added a shroud ring, or box fin, to the tail, which greatly improved its stability in the air and water. These changes transformed the Mark 13 from a terrible weapon into a great one. It became the standard aerial torpedo for the U.S. Navy and played a huge role in the naval battles of the Pacific. So, the story of the aerial torpedo is not just about the weapon itself, but about the small, often simple additions of bits of wood and, metal work that made it work. It was a story of aeronautics and hydrodynamics, of solving the complex problem of transitioning a weapon from the air to the sea. But what parts of this story are still murky? The development of the Japanese torpedo modifications for Pearl Harbor was a top secret project. Are there lost research notes or test reports that would give us a more detailed picture of the trial and error process they went through? On the American side, the initial failure of the Mark 13 torpedo was a major scandal. How many attacks failed and how many air crews were lost because of this faulty weapon before it was fixed. the official reports might not capture the full extent of the problem. The small fins and rings were the key, but the full story of their development might be more complex than we know. Number 4, how did a farm implement help win the war? The battle against the U-boats was not just fought on the high seas, it was also fought in laboratories and workshops. One of the most effective yet simple anti-submarine weapons was not an explosive, but a device that looked like a piece of farm equipment. It was a depth charge thrower, and it was nicknamed the Squid. The Hedgehog mortar, which fired its projectiles forward, was a huge improvement over the old depth charges that were rolled off the stern. But the Hedgehog had a weakness. Its projectiles only exploded on contact. If they missed, they did nothing. This meant that a near miss, which could still damage a submarine with a conventional depth charge, had no effect with a Hedgehog. What was needed was a weapon that combined the forward-throwing capability of the Hedgehog with the destructive area effect of a depth charge. The Squid was the answer. It was a 3-barreled mortar mounted on the bow of a ship. The barrels were slightly offset from each other. It fired 300-pound projectiles at a time. These projectiles were not contact fuze. They were set to explode at a specific depth, just like a standard depth charge. The Squid was linked directly to the ship's ASTIC system. The ASTIC would determine the range and depth of the U-boat. This information was fed automatically to the Squid's fire control system. The mortars would be aimed, and the fuses on the projectiles would be set, all without human intervention. The firing officer just had to press a button. The 3 projectiles would land in the water in a triangular pattern about 40 yards on a side. They would then sink and explode at the U-boat's predicted depth. The result was a simultaneous 3-dimensional blast that was almost impossible to escape. A U-boat caught inside this triangle of explosions was almost certainly doomed. The Squid was developed in Britain and introduced into service in 1943. It was incredibly effective. A Royal Navy study of anti-submarine attacks during the war showed that the Squid had a kill rate of over 50%. This was far higher than either depth charges or the Hedgehog. It was the most lethal anti-submarine weapon of the war. Its success was due to the combination of forward-throwing, automatic depth setting, and a pattern of multiple explosions. It bracketed the target in a cage of high pressure. The Squid was a purely functional, unglamorous weapon. It was a heavy, awkward piece of machinery on the forecastle of a destroyer or frigate, but it was a precision killer. It took much of the guesswork out of submarine hunting. The ASTIC operator found the target, the fire control computer aimed the weapon, and the Squid delivered the fatal blow. But what are the missing pieces of the Squid story? The automatic link between the sonar and the weapon was a major technological step. So, how many technical glitches and failures occurred during the development and early deployment of this system? We know the statistics of its success, but how many times did the system fail, firing at the wrong time or at the wrong depth setting? And were there any instances of premature detonations that damaged the firing ship? The Squid was a brutal and effective weapon, but its operational history, especially its early teething problems, may be more complex than the simple success statistics suggest. Number 3, what if your computer was made of gears? In a naval gun battle, hitting a target miles away that is moving, while you yourself are on a ship that is also moving, rolling, and pitching, is an incredibly complex physics problem. By the time your shell travels the several miles to the target ship will have moved a considerable distance. You have to aim not at where the ship is, but where it is going to be. This is the problem of fire control. In the early part of the 20th century, this was done with charts, slide rules, and human guesswork. It was slow and inaccurate. What was needed was a machine that could solve these complex ballistic equations in real time, a computer. But this was long before the age of digital electronics. The computers that solved this problem were not made of silicon chips and transistors. They were made of gears, cams, shafts, and wheels. They were analog computers. One of the most sophisticated of these devices was the U.S. Navy's Ford Mark I fire control computer. It was a mechanical marvel, a metal box filled with an intricate web of moving parts. It was designed by Hannibal C. Ford and his Ford Instrument Company. The Mark I was a 7-ton mechanical brain. Information was fed into it by sailors turning dials and cranks. They would input the range to the target from a rangefinder, the bearing to the target's speed and course estimated by the operators and their own ship's speed and course. Inside the computer, this information was processed by a series of incredibly complex mechanical devices. There were integrators that could calculate rates of change, and multipliers that could multiply two changing values. Special three-dimensional cams were shaped to represent ballistic tables, accounting for things like air resistance and the spin of the shell. As the input dials were turned, shafts would rotate, gears would mesh, and levers would move. The output of the machine was a continuous, real-time calculation of where the guns should be pointed, in both elevation up and down and azimuth left and right, to hit the target. This information was sent electrically to the gun turrets, where hydraulic motors would move the massive guns to match the computer's solution. The Mark I and similar analog computers like the British Admiralty Fire Control Table revolutionized naval gunnery. They allowed battleships and cruisers to engage targets at immense ranges with a degree of accuracy that was previously unimaginable. During the Battle of the Surigao Strait in 1944, the USS West Virginia, using its modern radar, and Mark I computer, was able to score hits on a Japanese battleship from a range of over 22,000 yards in the middle of the night. It was a feat that would have been impossible just a few years earlier. You know, these mechanical computers were the hidden brains of the battleship. They were marvels of precision engineering built by skilled watchmakers and machinists. They were a forgotten branch of computing history, a dead end in the evolution of technology, but in their time, they were the state of the art. But what is the secret life of these mechanical brains? They were incredibly complex and required constant maintenance and calibration. How often did they break down in the middle of a battle? The grease and oil they required, combined with the heat and stress of combat, must have made them prone to failure. The official histories praise their accuracy, but are there ship's logs that tell a different story of frustrating malfunctions and missed opportunities? And what happened to these mechanical marvels after the war when they were replaced by electronic computers? Were most of them simply scrapped, their intricate gears and cams melted down, their secrets lost forever? Number 2, how do you fool a radar? Radar was a war-winning technology. It allowed ships and planes to see in the dark and through clouds. It could detect an enemy force from miles away, giving precious time to prepare a defense or an attack. But as soon as one side develops a new sensor, the other side starts trying to find a way to counter it. How do you hide from an eye that can see for 100 miles? One answer is to blind it, another is to confuse it. The technique that was developed to confuse radar was simple, cheap, and surprisingly effective. It was given the code name Window by the British and Chaff by the Americans. It consisted of bundles of small, thin strips of aluminum foil. These strips were cut to a specific length, usually half the wavelength of the enemy's radar. When these strips were dropped from an airplane, they would disperse in the air and float down slowly, creating a large cloud. To a radar set on the ground or on a ship, this cloud of aluminum strips would look like a large solid object. It would return a powerful echo, just like a formation of bombers or a fleet of ships. The idea was first proposed by the British scientist R.V. Jones, a key figure in the Battle of the Beams, the electronic warfare contest between Britain and Germany. The science was simple, but both sides were hesitant to use it. They were afraid that if they used it, the enemy would quickly figure it out, copy it, and use it against them. It was a weapon that could be easily turned. This led to a strange standoff where both sides had developed the technology but were too afraid to deploy it. The British were the first to use it on a massive scale in July 1943 during a bombing raid on the city of Hamburg. The bombers dropped huge quantities of window. The German radar operators on the ground were completely blinded. Their screens were filled with a snowstorm of false echoes. They couldn't tell the difference between the chaff clouds and the real bombers. The anti-aircraft guns and night fighters were rendered useless. The raid was a devastating success, largely due to this simple countermeasure. Chaff was also used in naval warfare. It could be fired from rockets or shells from a ship. A cloud of chaff could be used to create a false target, drawing fire away from the real ship. It could also be used to create a ghost fleet. By having a small number of planes drop chaff in a specific pattern, you could make it look like a large invasion fleet was approaching from one direction, while the real fleet was actually somewhere else. This was used as part of the deception plan for the D-Day landings, to make the defenders believe the main invasion was coming at the Pas de Calais, not in Normandy. Chaff was a classic example of asymmetric warfare. A few pennies worth of aluminum foil could be used to confuse a multi-million-dollar radar system. It was a low-tech solution to a high-tech problem. It didn't destroy the radar, it just gave it too much information to process. It played on the fundamental limitations of the technology. But what parts of the chaff story have been blown away by the winds of time? The decision to finally use window was a huge gamble. What were the high-level debates and arguments that preceded this decision? There must have been fierce opposition from those who feared the consequences of the secret getting out. And how effective was it really? While it worked brilliantly at first, the radar operators must have developed techniques to try and distinguish real targets from the chaff. Are there German operational records that detail how they tried to counter this new tactic? The story of chaff is often told as a simple success, but the reality of the electronic battlefield was likely a much more complex and evolving game of measure and countermeasure. Number one, what if a bridge could be built from a box? Logistics are the foundation of any military campaign. You can win the battle, but if you can't get supplies to your troops, you will lose the war. A key part of logistics is crossing obstacles. A river, a ravine, or a destroyed bridge can stop an entire army in its tracks. Armies have always had military engineers who could build bridges, but this was usually a slow, custom process. During the war, a British civil servant and engineer named Donald Bailey designed a revolutionary solution to this problem. It was a prefabricated modular bridge system. The idea was to create a bridge out of a small number of standardized interchangeable parts that could be assembled quickly, by hand, without the need for heavy cranes or machinery. The core of the system was the Bailey panel. This was a 10-foot long, 5-foot high, rectangular panel made of welded steel. It was light enough that it could be carried by 6 men, but it was incredibly strong. These panels were the building blocks of the bridge. They could be pinned together end to end to create the 2 main girders of the bridge. For a longer or stronger bridge, you could bolt a second or even a third row of panels on top of the first. You could also bolt extra panels to the sides, creating a thicker, stronger girder. This was the genius of the system. You could tailor the strength of the bridge to the specific gap you needed to cross and the load you needed to carry just by adding more standard panels. The roadway, or deck, was made of wooden planks that were laid across steel beams called transoms. The Bailey Bridge could be assembled on one side of a gap and then pushed or launched across to the other side. The engineers would first build a slightly tapered launching nose on the front of the bridge. This would lift the front of the bridge up as it was pushed across, so it wouldn't dig into the far bank. As the bridge was pushed forward, new sections would be added at the back. It was a simple, elegant, and incredibly fast way to build a bridge. The Bailey Bridge was adopted by the British and American armies and was used in every theater of the war. It was a logistical game changer. When an army came to a river and found the bridge had been destroyed, they no longer had to wait for weeks while a new one was built. A company of engineers could erect a Bailey Bridge in a matter of hours. This allowed the pace of the advance to be maintained. They were used to cross countless rivers in Italy, France, and Germany. In the Burma campaign, they were essential for crossing the jungle ravines. The Bailey Bridge was not a weapon. It didn't fire a shot or drop a bomb, but it was one of the most important pieces of military equipment of the war. Field Marshal Montgomery is said to have claimed that the Bailey Bridge was one of the 3 key technological developments that helped win the war, along with radar and the heavy bomber. It was a simple, brilliant idea that solved a fundamental problem of military logistics. But what are the forgotten stories of the Bailey Bridge? The design seems perfect, but were there early prototypes that failed catastrophically during testing? The speed of assembly was a key feature, but this must have put immense pressure on the engineering units. How Many accidents and injuries occurred during the rapid, often under fire, assembly of these bridges. And finally, the bridge was made of thousands of small interchangeable parts. What was the logistical story behind manufacturing these millions of panels and pins and getting them to the front lines? The bridge itself is a symbol of connection, but the full story of its own supply chain may still have some gaps.